Okay, I think we can start this last session of the day with Alberto Les, who will be talking about data analysis with gravitational waves. So the floor is yours, Alberto.
Okay, hi, and thanks for the invitation. So as mentioned, I will introduce some libraries in Python for gravitational wave data analysis and to probe different resources available, especially in the Gravitational Wave Open Science Center. So gravitational wave data analysis is, sorry, I removed my Slack so I can. Okay, so I will mostly speak about three libraries. The Gravitational Wave Open Science Center library, which provides an interface to query for open data, so data which has been publicly released. And I invite also the readers to click on the link in the notebook to check all the resources put by the LIGO and Virgo community to introduce beginners to gravitational wave analysis. And you can find also download data from there, both in the original gravitational wave frame files or in HDF5 files, which can be used, processed basically in every language. The second library I will speak about is the gravitational wave PI package, which is a useful for time and frequency domain analysis. It's mostly used for pretty straightforward analysis, but it can give a flavor of the possible things we can do with gravitational wave data. Finally, there is the PyCBC library, which is more of a complex library, and it's used in real pipelines, so in online search pipelines, and that's also contributed to many important discoveries in the LIGO and Virgo community. And we will use this library to show how to generate waveforms and search for different detector characteristics, antenna patterns, and to compute what is called the matched filter time series. So let's go through the notebook. I'm just importing some stuff here, which some of them I will use, some of them actually not. But and then we have the three libraries I spoke about. So and we can check the versions of them to see if they are up to date. And this is important, especially because there is reference to catalogs inside these libraries, and they are updated with new events every now and then. So the first thing we want to look at is the Gravitational Wave Open Science Center library to query for data from gravitational wave events. And we import some specific modules and methods. And the first one I want to look at is the find datasets function, which we can check with the Python magic. Accepts a number of keys, such as the detector type, and here we can choose, for instance, event to search for events, or catalog to search for a specific catalog of events, and a number of other keys. You can look through it in detail just by checking the full documentation. Let's see how this works. For instance, let's say we want to look for some data from the Virgo detector, and what we do here is use these find datasets and choose the Virgo detector as key, and we see the output is a list with all different events named with a convention which is uses the year, the month, and the day. And You can see there are different versions even of the same events. Generally, the latest is the highest number. And you can see also that there are some specific other keys referring to discovery papers or to specific events. We can then use the same function, for instance, to print all the different types of catalog available by choosing the type catalog key. Let's see how that works. And we see that we have another list which provides all the different available catalogs. For instance, the gravitational wave transient catalog 2 is the latest catalog published in a paper with events from the latest science runs. We can then select one of a specific catalog and ask for all the events inside this catalog as an example. And you see here, there are a number of events which are printed out. So that you can use all sorts of combination to look for the specific event you are naming convention you're looking for. And this would be useful later on in the other libraries. You can also search for science run. So this provide pointers to full runs. So large data sets which last months. And you can see here all the different naming convention with also the sampling frequency for different analyses which require higher or lower sampling frequencies. Okay. Then we can print, we can look at the run segment function. And this provides basically the GPS starting and ending time of the run. And you can just do a brief calculation here and also check how much effectively a science run can last. And now we can take an event from the above list, for instance, and print its GPS starting time. And you see here, there is the output. This is useful if we have the data which we downloaded and want to go at a particular time where we have the gravitational wave event. And this is a straightforward way to do it with the Gravitational Wave Open Science Center library. Okay. So we have shown these simple tricks, and now we can also pick up one of the events and use the locate get event URLs function which prints out the URL at which the URL, sorry, at which we can download the files referring to these specific events. So just by copy and pasting this even into your browser, you can just simply download the selected data file which you wish to have in your computer. And this is, you can see an HDF5 file. So this is a very simple library, and it's not used for actual analysis, just for querying data. I just showed some of the possible things we can do with this library, but I want to move on to more actual data analysis stuff. And this is the gravitational wave Python library. And we use this to access and analyze data sets in the time and frequency domain. So let's, for instance, check some of the possible functions inside. And the fetch open data is the first function you should look at. And it's used, okay, just a second. Need interesting. Okay. Okay, I hadn't run, right. Okay. Okay, now you can see the convention and how to use the function. So you have the interferometer, the start and ending GPS times of the segments you want to retrieve. You have the sampling rate. We generally take it at 4K for most analysis. And you have another number of possible keys which you can insert, such as the version, which we saw before for the events, or the place where the data is hosted. And in this case, by default, they are all from the Gravitational Wave Open Science Center. Okay, so let's see the usage of this. And in particular, we want to fetch the data for the event gravitational wave 190521, which we have previously defined here above. So we take the GPS of the event and choose a length of seconds for the window we want to retrieve. And let's see what this produces. So the operation can take some time because the data has to be fetched. The verbose here key means that we produce some output, like with the information about this segment. And you can also directly download the data on your machine by using the cache equals true option. So let's wait for this to finish. Just a second. And after we will have retrieved the data, what we will do is try to see how this data looks like in the time domain, and then carry out some analysis in the frequency domain. I don't know why this is taking so long. In the meanwhile, is the notebook working for people who are following the lecture?
So it's working for me. Some people had issue with Windows because the packages are not in Conda for Windows, but it seems to be working with pip install.
Okay. I don't know why this is not loading.
So how big is this data?
It's not that big. It's sampled at 4 kilohertz, and it's 32 seconds, so it should be fairly small, actually.
Maybe the HTTP connection is stuck. You know this trick with hitting II?
Sorry?
If you hit twice the I key when the cell is selected, it triggers a Control-C. So you can just, if you now just press II 2 times, yeah, and then just relaunch it. Okay. It's basically if you type Control-C, so keyboard.
Yeah, so you mean I rerun it?
Yeah, I would try it. Sometimes the HTTP connection is just
yeah, maybe I can also just reduce also the segment. It's not. Okay, yeah, probably that's stuck in some way. Let's try to go out with just a 16-second window. And let's see how this data looks like. Gravitational wave PII library used this time series and frequency series, and we see that this inherits from the AstroPy, its doc strings, and let's see the function which is used, defined in gravitational wave PII for plotting, which is pretty similar to the matplotlib function actually. And there is a scaling with the GPS, which is possible. And let's see just for the sample strain. Okay, so here is the output. You see the strain. Gravitational waves are very small in amplitude. And actually, this is much larger than the actual amplitude of the gravitational wave. But what you see here, you have in the X label the time with the UTC and GPS time. And this is an example of plotting with the gravitational wave PII library. Then after we have plotted the signal, the stretch in the time series, we can also think of pushing to the frequency domain where the spectral content of the signal is visible. And let's do this. Okay, so this is just applying a simple fast Fourier transform to the time series we just fetched. And you see that this is just a simple fast Fourier transform on the whole segment without windowing and stuff. So things looks kind of strange compared to what we expect actually to see in the frequency domain. What we can do here is apply some sort of windowing, and you've probably seen this in the SciPy lecture. So we download the SciPy window. We get the window and we choose here the Han window, for instance, and just multiply our data and produce the same plot. I don't want to go too much into these details actually, but this is the output, which is slightly different. But this is still not good practice, applying a single fast Fourier transform window, even if it's windowed. So what is generally done to analyze stretches of gravitational wave data is to compute the amplitude spectral densities using an averaging method. And this can be directly done with the gravitational wave PII library, and in particular with the amplitude spectral density implementation. So let's see how this works. So you can see here the possible parameters, such as the fast Fourier transform length, the overlap between the different fast Fourier transforms, the window choice, and even here you can give your custom window, and the averaging method for the amplitude spectral density computation. And you can use here mostly three methods, I think. Yes, the Bartlett, median, and Welch method. So let's see how this what this produces. I just set some custom limits in them to focus on the interesting range for gravitational wave analysis, where gravitational wave data actually has a meaning, so above 10 Hertz. And also I set the epsilon range and the y-axis range accordingly to the desired interval. So let's see what this produces. Okay. So this is the typical sensitivity curve of a gravitational wave detector. And you see that it's much smoother to the ones you can see here. And this is due to the averaging procedure with computed over different small segments. And you also have the option to use native colors for the three interferometers, which are fixed. in the LIGO Virgo community. So here I showed, for instance, one of for the LIGO Livingston. And yes, so what you see here is basically the amplitude spectral density of a gravitational wave detector. And in particular, you can see some structures. For instance, these peaks, which are due to particular noise lines, which are known and analyzed and tracked during the analysis. They can change in shape, in amplitude, and also in frequency, actually. And the overall morphology of this curve is dictated by different contributions, mostly noise contributions, which are seismic, Newtonian noise, thermal noise in the interferometer, or the so-called quantum noise. And you can click here on this link for specifics on these particular lines you're seeing here. So this is just to give a flavor of what gravitational wave data looks like, and what an interferometer in amplitude spectral density curve looks like. So as an exercise, if people want, you can just try to plot the different interval for other interferometers and just compare the sensitivity of the different interferometers. And you can do this just by simply changing the request in the fetch function we provided at the beginning. There are solutions in the last cells of this notebook. So we move on, and after we have seen the signal in time and frequency domain, we actually haven't really seen a signal. We just saw some data. And to really see a signal inside this data, we use time frequency representations. Obviously, there is some pre-processing involved, such as whitening and filtering, high pass and low pass filtering of the data. So a number of processes which I don't want to go into the details of, but obviously are there. And what we will build now is a time frequency representation, which follows the frequency evolution of the data. And you can think of this as computing multiple amplitude or power spectral densities in time, and just see how the frequency content evolves. And this can be done with the gravitational wave Python package with two functions, actually. And I just show one of them, the spectrogram 2. And you can see that this computes a non-average power spectrogram of the time series. And sorry, you can still choose the fast Fourier transform length and the window. Let's try to apply this to the data we fetched. Okay, so this is what we see at first. Obviously, this is not so good. And the fact is that the scaling on the color bar affects the image we see here, because the values are spread out through multiple orders of magnitude. So we just set this, I prepared this small adjustment, and this resets the color bar, the limits, and uses a logarithmic normalization. And if I did this right, it's slightly better. I mean, you still can't see anything. You see some lines here. You see some very high values at the low frequency end, and this is what we also saw before looking at the actual amplitude spectral density. So this is expected, and you see sort of see some of the noise lines I showed in the previous plot. but you can't really distinguish a signal, which should be there. So what is done generally is to use other methods for the production of the time frequency image. And in particular, multi-resolution methods such as the wavelet transform or the Q-transform, which involves logarithmic tiling in the time frequency domain. And I left the reference if you want to click on it for the paper. Let me go back to my Jupyter notebook. Okay, so the idea is that in the Q-transform, you have different resolution in time for the different frequency bands. So this is useful because for lower frequencies, we can reduce the time resolution. And just to show that the Q-transform can directly be implemented in the gravitational wave Python library, and you can set a number of values, such as the Q range, which is rather technical, but you can choose the frequency range, and you see here the default is from 0 to the highest possible frequency, and another number of possible values. And you see here there is the whiten parameter, and this means that the data is whitened in the process. Okay, so let's see how the Q-transform applied to the data we previously plotted with the usual Fourier method produces. And we see that this is very different. Obviously, the whitening does its part, obviously, but you can see this this blob, which is actually a chirp signal, and yes, a pretty short chirp signal happened at LIGO Livingston, and this is the actual gravitational wave signal from a binary merger. I want to point out that there is this particular key which you have to set, and it's useful to zoom into the signal. So I can, for instance, show what happens if I change this. Yeah, I zoom in the signal, and if I take a too large range, the signal will be barely visible. Let's say 3. That's for an experiment. Okay, I mean, in this case, it's visible, but you can't really distinguish the chirp from other types of instrumental noise, such as so-called glitches. So let's go back to our previous configuration. And as I mentioned, you can change the frequency range. You can adjust to have the best possible image in your opinion. So let's stick to 100. Okay. So this is very straightforward, as you can see. And you can use this for any kind of signal, any event you can look at with the Gravitational Wave Open Science Center library, and play with it a little bit if you want. You can also do the same experiment for other interferometers. And let's see if this works. I think I have to fetch the data first. Okay, so I will leave you with doing this on the Virgo interferometer. So basically, you can just run this code, but previously you have to fetch the data, as I did for the LIGO Livingston interferometer. So I left another exercise here for the audience, in case they want to play with the notebook. I switched to a famous event, the gravitational wave 170817, which corresponds to the binary neutron star merger. So the first multi-messenger observation in the gravitational wave and electromagnetic messengers due to a binary neutron star. And if you want, you can try to complete the following steps. Fetch the data for all 3 detectors, plot this Q transform, and you will have to play a little bit with the frequencies and the Q range to have the signal visible. And you have to take into account the binary neutron stars signals are longer, so are visible for a longer time, and that their frequencies are different from the binary black hole mergers. So after you produce the plots, you can answer in which detector the signal is clearly visible. And you will see something strange happens for the LIGO Livingston data. And you can answer the question on what's happening to this data, maybe also checking the original papers if you don't have ideas on the subject. Okay, so this was a very brief overview of the gravitational wave Python library. I want to now switch to the PyCBC library, and as the name suggests, this is used mostly for the analysis of compact binary collapses, but has a number of functions and methods which are useful to also for other kind of custom analysis. For instance, I'm using some of these functions when I'm studying injections of supernovas in data. So I'm importing a number of methods from this library, and in particular, we'll focus on the detector method to study different detectors and see what we can retrieve, which information we can directly retrieve from PyCBC. And also we will produce a waveform using the get time domain waveform function. And I will show this now step by step. Okay. So as a first step, we start from we want to produce a waveform, a custom waveform, given some source parameters. And you have a large number of source parameters which determine the actual waveform. And we're speaking of a compact binary collapse waveform. And if some of you have seen gravitational wave data in the past, this corresponds to so-called chirp signals, which have an increasing amplitude and frequency in time up to the merger. Afterwards, you have a ring down phase, so the signal dies down exponentially. So the function get time domain waveform produces 2 outputs, which are the 2 gravitational wave polarization, which describe the gravitational wave, the plus and the cross polarization. Among the possible parameters which we can set, there are the component masses of the binary, so the first and second mass of the black hole or neutron star. And there is the sampling frequency, in case our analysis is at higher sampling frequencies or lower sampling frequencies, but this is generally best to produce them with a lower sampling frequency. So 4 kilohertz is generally perfect for most analysis. And you can set a lower limit for the gravitational wave frequency of the chirp, and this basically affects the length of the template. The lower the frequency, the longer the computational time needed will be to produce the actual waveform. And then you can set the distance. The distance is in units of megaparsecs, while the masses are in units of solar masses, and then you have other things such as the spins, which I did not include, and by default are 0, and the inclination angle of the binary. So if we are looking at the binary plane face on, or it's inclined with respect to the line of sight from the observer to the source. And this is given in radians. So let's see. First, let's check this function. Great. Yes, I did not run here. Okay, so you can see all the different possible parameters which you can insert here. Using the default generally is fine. We show here an example. So we have produced here the two polarization, which are PyCBC time series objects. And we can directly plot these objects with matplotlib pyplot, for instance, which I imported as PLT. And we see this is the typical chirp signal. So you start from a certain phase, which is fixed by the frequency you chose. And you see that there is an increasing amplitude up to the merger. And this is for a 12 and 15 solar mass binary. You can also plot the individual polarizations. Let's show what they look like. So these are the individual plus and cross polarization for the signals. And you can see that I used here the syntax to plot the sample times for the associated to the polarization. And you can see that the merger is typically set at 0. But you can also, in case of real analysis, use GPS times. And we will see later how this works. And now we switch to detectors. And PyCBC has some very useful functions, I think, for custom analysis, which allow you to produce signals, as we have just seen, so custom waveforms, and inject them into detector data, which you can either take from the available public real data, or also create in a custom way, just starting from a detector noise sensitivity curve. And you can inject the signals by using the functions available in PyCBC, which take into account a number of subtleties, including the location of the detector, which affects the antenna pattern of the interferometers. Let's go through these cells and show what happens. So first of all, we can print all the available detectors simply by using the get available detector methods. And you can see them here. So you have the most important ones here, the advanced detectors, which are running at the moment, which are the Virgo, and the two LIGO detectors, L1 and H1. And you also have a number of locations for other kinds of detectors, such as resonant bar detectors, or the geo detector in Germany, for instance. And we can look more into these detectors and retrieve interesting quantities, such as their position, so their latitude and longitude. And what I'm doing here is simply running through this detector list and using the detector function, which retrieves the information for the particular detector, and we then print it out with a simple print command. And we can see here what what is the output. And the units used here are radians, obviously. And for instance, you can see the Virgo latitude and longitude, or the LIGO, the two LIGO detectors position on Earth. Okay, so then there is a Qt function, which I sometimes use, and it's very educational. I'll let you guys discover it. And it's the light travel time to detector. Sorry. Travel time to detector function. And this allows you to print out the travel distance of light, the travel time of light between the distances of the different detectors. And it's needed when you want to take into account a signal, a candidate signal in a coincident analysis. And in particular, this gives you the delay between the different interferometers. You can really carry out a coincident analysis with the different data sets. Okay, so I'll leave that task to you. And now we want to try to take the two polarizations we obtained from the previously generated waveform and project it into a specific detector. So as I said, each detector has its own antenna pattern, which gives the sensitivity to the two gravitational wave polarizations at a specific time. So as you can imagine, the detector is on Earth and it's rotating, and the antenna pattern to one specific right ascension and declination, so one sky position of the source changes over time due to the relative orientation of the source and the detector. So we can directly compute this antenna pattern function with the gravitational wave, PyCBC. And I just want to note one thing, that since we are dealing with the burst signals, we can just compute this antenna pattern function factors once, because we assume that they don't change enough in time for the signal to actually need different weighting each at different times. So let's see how this works, maybe. Okay, so the inputs are the right ascension and the declination of the source, the polarization angle, and the specific GPS time. And the GPS time is at Earth, obviously. And let's see how this works. First, let's see an example. We choose a specific right ascension and declination. Let's fix to 0 the polarization. A specific inclination, and a time. So then we reuse the code, we re-report the code we previously used for to produce the waveforms, which we showed above. And what do we do then? We choose a detector, define a detector with the detector function, and we simply use the antenna pattern function in this way, providing the quantities we just defined. And let's see if there's something else of note. Okay, let's first run this. Okay. So what have I done? I produced the antenna pattern function, and you can see them here, the actual values, which weight the two polarizations, which are then added to produce the actual signal. There is an alternative, which is to use the project wave function, which directly projects the signal given the two polarization, and this is has given the produced image. And in this case, you can see that the time reported is the one I provided here. So the signal is added with its specific times. Okay. You can try to see how the signal, this particular waveform changes if I project it on different detectors. And I leave that as an exercise for people who want to do that. And you might see that the same signal will have a very smaller amplitude, obviously for Virgo, but this may be due to another factor, which is the fact that the particular direction in the sky might not be a particularly favorable direction for Virgo at the moment. Okay, so I want to finish by showing a nice computation of the matched filter SNR, which is the quantity which is used in gravitational wave searches to look for signals. And I import a number of methods and functions. And we'll show an example on a specific gravitational wave signal, the GW170814 signal. And the idea is that the matched filtering procedure, for those who are not, who don't know this particular method of the data analysis for signal detection and extraction, is based on the fact that we have a template, which is a possible gravitational wave signal in time or in the frequency domain. And we use this template and try to match it to the data stream. The idea is that when this signal is accurate and matches a real gravitational wave signal, we expect a spike in the so-called signal-to-noise ratio matched filter time series. So let's see how this works. First of all, I want to show that also in PyCBC you can list events and access catalogs. So this is a similar function to the Gravitational Wave Open Science Center one. And also in the Gravitational Wave Python, if I recall, you have a similar possibility, but I didn't look into it before this lecture. So you have the event names here, and interesting thing you can see is that also here you have the versions of the events, but I don't need the full name. I can just put out just a simple event name for an analysis. So in this case, it was gravitational wave catalog 2. But we can also take the first one, and you see here the event which I selected. Okay. So now what I will do here is a loop into the 3 interferometers. I will read the data. I will high pass it with the high pass filtering function, and let's first run this, and it's okay, it's working, which I previously downloaded, imported. And so how does this work? We define the merger, and we actually define it inside the loop because to query the actual strain, we have to give the interferometer in which we want to observe the data stream. So in the first loop, you will have the Virgo, then you will have the LIGO Hanford and the LIGO Livingston each time. So the data is retrieved, and you can also see the merger time in the different interferometers just by querying with the time syntax. And after you have high pass filtered the data, I just copy and pasted this procedure from a tutorial, so I didn't actually fix the details of the high pass filter. So we compute the noise spectrum around our signal, and this is used in the matched filtering procedure because what I didn't mention before is that you match the data with your template for the gravitational wave signal, but you apply a weighting which takes into account the noise content of the interferometer. And this is intuitive in the frequency domain. And as we showed before, one of the frequency curves has one of the amplitude spectral density of the interferometer has very high noise amplitude at lower frequencies. Then you have a smaller amplitude at central frequencies, and then the amplitude goes back up. So there is a weighting which is applied accordingly to compute the best matched filter SNR. So this is just a whitening procedure, and then you can apply some further smoothing with the high pass and low pass filter. Okay, on the whiten strain. Here it's just an if loop for the different colors available, and then I produce a subplot in matplotlib, and just plot the actual signal. I fix accordingly the limit in the x and y axis. And you can see that in the y-axis there is not the actual strain, but it's normalized to some degree because of the whitening. And this is similar to the code which was used to produce plots in some papers. Okay, so I already ran this, but I'll run it again. And you can see here the output. And I just put the legend for the audience. And the signal, it's actually this one. It's not a very high SNR signal, not so visible. And but it is an actual 3 interferometer detection, which might sound strange because in the Virgo especially data, you can't really appreciate the signal just by looking at the whitened data. You can kind of do it in the LIGO Livingston and LIGO Hanford here. And this is the signal. Obviously, you still have the GPS times in the x-axis. And just as a final step before the end and the questions, I just run the code for producing the matched filtering. And in this case, I need a template. So I use a similar function to the one I previously defined for generating time domain waveforms. And in this case, it's the generate frequency domain waveforms, because that is the template which is used in the matched filtering procedure and in the matched filter SNR computation. So even here, I selected some very specific masses, which are the ones of the actual, which were estimated with the parameter estimation. So I'm kind of cheating on that. and you just produce the matched filter time series, providing the noise PST, which we computed above. You can set a low frequency cutoff, obviously, and then you do this step, which is just removing the regions where there is filter wraparound. So basically, the filter which runs into the data is shifted every now and is shifted every time to compute the signal to noise ratio time series, but obviously you have a discontinuity at the end, and therefore there are spikes in correspondence to these discontinuities. So we remove and just center into the region where we expect to have the signal. And this produces the following plot. And so this is the signal to noise time series. You can see that there is an average value, which is about around 2. And the spike in correspondence to the actual time of the merger. Okay, so that's all from my side. I think I went a little bit long, maybe on time. I'm sorry about that. And I left down here the solutions to the different tasks. Maybe don't just read them directly and first try to actually do the exercises. So if you have questions, I'm here, available, and thank you again.
Thank you very much, Alberto, for this introduction to gravitational waves analysis. I don't see any question in the chat. So I will have maybe a similar question as I had for the neutrinos on open data. I think that all data are also from Virgo and LIGO are open, right?
So at the moment, surely from the first 2 science runs, and I'm quite sure from O3A. I'm not sure about O3B. Yes, so the O3B data, so the last part of the latest science run is still being analyzed, and I think in the future there is some idea to release them directly as a real observatory, especially from the LIGO counterpart. But I'm not, at the moment there is some lag between the actual end of the science run to allow for analysis of the collaboration, which I don't know if it's 6 months for some specific data. And also in this analysis, I only showed the actual strain data. So the real data has a number of different channels which also monitor and keep track of the different parts of the instrument. And these are useful, especially if you have to remove noise artifacts from the analysis. And so, yeah, I wouldn't say that the data is really completely public, but data from the older science run can be analyzed virtually by anyone.
That's cool. And
you can see the, sorry, I didn't want to interrupt you. I don't know if you can see the screen at the moment.
Yes, we can.
Okay, so you have the Gravitational Wave Open Science Center where you can directly download data, and just to give you a glimpse, there is the download data page. You can go in events and catalogs, and there are the different data releases here, documentation, timeline. For instance, this is the latest one, the 4 kilohertz data. And just to show maybe people, you can select an interferometer, put a start time, for instance, in GPS or whatever, and you can directly download the data in HDF5 files. And let's see just an example here, maybe.
I don't know if I just put something random. And there is also the data quality guide, which allows people to check if the segments are good. When you see numbers 100, it means that the data segment is good. And then you can just click here and download the data on your computer. But you can also do it with the fetch data functions, which are provided.
So that's great. Yeah, the portal is yeah, really nice. And do you have an idea of the volume that all the data represent?
Sorry?
Do you have an idea of the volume that all these data represent for O1, for example, or O2?
Well, actually, not really. I don't have that number straightforward, but you can see that they are divided in around an hour of data. And for instance, like O1, each file there is the dimension of the file. So good data is about 125 megabytes, and you can try and keep track of how much of those are many gigabytes. Not terabytes though, so.
Yeah, that's still manageable.
Yeah.
Okay, thanks for showing this portal and for the whole lecture, of course.
Thank you.
Okay. Last maybe announcement. So tomorrow we will have the machine learning lectures all day. To prepare that, I think you just have to git pull. The material has been added to the repository. And you should not have anything else to install, sorry. And also a reminder that tomorrow morning we will have a group picture during the morning coffee break in Gathertown. If you want to participate in that will be a virtual group picture. And yeah, that's it. So thank you very much for this day, for all the teachers of today, and see you tomorrow.